All right, let's take a look at lesson 4.2 and 4.3, proving triangles using proofs. Yesterday we introduced in our previous lesson we introduced the triangle congruences using side, 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 the side angle side congruence, the angle side angle congruence, and the angle angle side. So now we're going to take a look at proving triangles congruent by using a proof. So as before, when we first learned about proving triangles congruent, we had to prove that all 6 corresponding parts were congruent. And yesterday we learned the shortcuts. So now we're going to look at how we can prove these triangles congruent with only having to prove 3 statements of congruency instead of 6. So like we've done before, in the first step of a 2-column proof, we're going to have it broken down to statements and reasons. Statements are what we know, and the reasons are how we know it. So we look up here at our given, and we have 2 things written up here. So we're going to write down these 2, LM congruent to NP. Okay, so you can combine them into one given statement or two. So we'll just go ahead and break these apart into 2 different ones. So this is our given statement. So how do we know it's true? Well, it was given to us. And then we look at our next one, LP congruent to NM. Okay. Now, in this one, it's also given to us. So now we have our first 2 given statements. We have a statement of segments here, 2 sides that have been given to us. And if they weren't marked already, we'd go ahead and mark them. So we have these 2 sides, LM congruent to NP, and then we have LP congruent to NM. So now we need either one other side or an angle. So if you look at our picture here, anytime we have the same side that's a part of both triangles, we can say that it's congruent by the reflexive property. So as we name this, we're going to say LN congruent to, and to do the corresponding parts here, you notice that there is an L congruent to N, and there's also an N congruent to L. This happens when our triangles are kind of reversed. And so what we're going to do is we're going to put this as NL. Okay, so LN is congruent to NL, and this is by the reflexive property. Okay. And so now let's take a look. We've got 3 side lengths. We have a side, side, and a side congruent to side, side, and side. So now we can prove our triangles congruent. So triangle LMN is congruent to triangle NPL, and our reason is going to be side, side, side congruence. So we can use just our initials, SSS. Okay, let's go to the next one. And some of these I'll have you work them out by yourself, but in the first few we're going to work together. So now we have one that tells us we have a congruent statement here, and we also have one where part of it tells us we have parallel lines. So we're going to start, once again, we're going to start off by writing down our given statement. So we have EF congruent to GD. Okay, so that's marked right here, EF and GD. So this is going to be given. Now the next thing they gave us is that we have EF is parallel to DG. These 2 sides are parallel. So what I'm going to do is I'm going to put a little arrow here to show that these are parallel, which was also given to us. And now what do we know because of our lines are parallel? Well, in 9 times out of 10 in these proofs, when we have parallel lines, we're going to be using this exact reason. So, parallel lines create, in a transversal, this line right here acts as a transversal, creates special angle pairs. And when it does that, when we have parallel lines, we know that creates those special angle pairs like alternate interior angles. These 2 angles right here are alternate interior angles. The way you can determine which ones are your angles are the ones that are created from the parallel line and the transversal. So if it touches the parallel line and the transversal, This is your alternate tier angle. This angle is created from the parallel line and the transversal. So now we have to name the angles. So up here, start with an angle on top. I'm going to name it angle EFD. Now you can't just name it an angle F because there's multiple angles at F. So once again, you got to use it by using the 3 points. Okay, so angle EFD is congruent to angle, and we're going to start with GDF because E goes with G, okay, F goes with D, this angle F right here to this D, and then D goes with F. So the way we say here is we say that the reason why these angles are congruent is by alternate interior angles. And alternate tier angles are congruent when lines are parallel. That would be the full definition. So let's look at number 4 here. So we've got and there should be 5 here. Okay, so we've got a side length, an angle measure, and now we have side length and an angle measure. So as we mark these on here, we have side length, angle measure. So now we need either another side or another angle. And so by looking at this, once again, we have a line congruent to itself. So we can say that this line is going to be DA congruent to, or excuse me, not DA, DF congruent to FD. And this is by the reflexive property. Okay, so now we have another side length, and so as we look here, we have a side congruent to another side here, so we got S. The angle is in between the two sides, so now we can say that our triangle EDF is congruent to triangle GFD. If you ever get confused on what parts match up, you can always look at what you're trying to prove, and you can see what angles or what go together. So E goes with G, D goes with F, and F goes with D. So EDF is the triangle over here on the upper left. This is the lower right. And our reason here is going to be side, angle, and side. All right, so when we have parallel lines, this is one thing you're going to use, is you're going to use alternate tier angles. So let's take a look at example 3. This one has 6 statements and 6 reasons. There's not a limit to how many statements and reasons you can have. You just have to make sure that you prove all the different parts. So let's look here. We have angle BAC is given to us as congruent to DAC. So that's marked right here and right here. It says as the AC is perpendicular to BD. So remember what perpendicular means. And we're trying to prove that triangle ABC is congruent to triangle ADC. So first thing I'm going to write here is our given statement, angle BAC congruent to angle DAC. We'll write given. Then we look at the second part, AC perpendicular to BD. Now once again, these don't have to all be in the same order. As long as your last statement is what you're trying to prove, then everything else can kind of be mixed up. But I like to do it as kind of a thought process here. So this is, once again, this is given. I got my first 2 given statements. So I have an angle measure right here. This is not a statement of congruency, it's just stating the fact that these are perpendicular. So remember, perpendicular means that we form right angles. So the logical step through here is once you determine that they're perpendicular, then you have to say that they are right angles. Okay, so we're going to say that angle ACB and angle ACD are right angles. And so this is going to be by the definition of perpendicular. Definition of perpendicular line. So we can use abbreviations as we go throughout here use the perpendicular symbol. So definition of perpendicular lines. Now once we say that they're right angles, and then we know that all right angles have a 90-degree angle. And so right angles are then congruent. So we're going to say now that ACB is congruent to angle ACD. And our reason is that all right angles are congruent. So that is another statement of congruency. So this is another angle, which means now we need to show that we have another side that's congruent. Because we don't have one that has three angles, we have one that has a side. So which side would it be? We've got two angles, and once again you have a side that is shared, so we can say that AC is congruent to AC, and this once again is the reflexive property. And so this is a side length, so we'll mark it here. So we have an angle measure, a side, and an angle measure. So now we can say that triangle ABC is congruent to triangle ADC, and our reason is going to be angle, side, angle. The side length touches both angles. It touches this angle right here, this angle right here, this one here, and this one here. All right, so those are the first three. So what I want you guys to do is I want you to pause the video now, and I want you to attempt to work number 4. Remember what happens when we have parallel lines. So you can go back and look at that example. Try to do it on your own. But in this case, in this problem, we're given that angle M is congruent to angle K. WM is parallel to RK, and we're trying to prove that triangle WMR is congruent to triangle RKW. So pause the video now, try to work out as much you can, and then come back and check your answers when you're done. All right, so we have our measure of angle M is congruent to angle K. That was given to us, and that's already marked on here. We have these are parallel, and so let's say the next thing we recognize was the reflexive property. So we would say that WR is congruent to RW by the reflexive property. So right now we have this angle and we have this side. So we have an angle here and a side congruent to an angle and a side. So we've got, I'll write an angle over here, we got a side length over here. So now we look to see what else we know. So remember when we have parallel lines, we have a pair of alternate tier angles. And so to make sure we mark those correctly, we need to make sure that we draw the angle in the right spot. Remember, it touches the parallel line and the transversal. So it should be this angle right here. And this right here touches the parallel line and transversal, so it's going to be this angle right here. So as we name it, we're going to say angle MWR congruent to angle KRW. That helps identify these two angles. And our reason is alternate tier angles are congruent. So now that gives us our second angle. Notice that the side length is not in between our two angles. It is the non-included angle, which means triangle WMR is congruent to triangle RKW by angle, angle, side. All right. I want you guys to try example 5. Using side, 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 you're going to prove that given that PQ is perpendicular to QS, RS is perpendicular to SQ, T is the midpoint of PR. Find that triangle PQT is congruent to triangle RST. So pause the video, come back and check your work when you're done. All right. So we're going to write here, and I combine the first given statement here to be one statement, since they're both about being perpendicular. If you didn't, you put it two separate statements, you'd have 8 statements and reasons. So PQ is perpendicular to QS, and RS is perpendicular to SQ. It's given. So remember when we talked about angles being perpendicular, that means that they're going to be right angles. So we're going to name these right angles. So since there's only one angle at Q and S, we can just say angle Q and S are right angles. Definition of perpendicular lines. Then we can come down and we have to say that angle Q is congruent to angle S. All right angles are congruent. So right here we have our first congruence statement, which is that angle Q is congruent to angle S, which is an angle. Then, let's say we recognize we have vertical angles. So we have vertical angles here. They're congruent, so we need to name them. So we have QTP is congruent to STR. So this is another angle that's congruent, which means that leaves us with a side length that we need to show that is congruent. These are congruent by vertical angles. So T is the midpoint of PR, so we have to go back and write this. This is given. Now what it means to be the midpoint, when you cut, if you're in the middle of something, they're going to cut something in half and you'll have two equal halves. Well, if PR has been cut in half at T, okay, if T is in the middle, it's cut PR in half, which means that this side is going to be congruent to this side, two equal halves. And so we have to name which halves are congruent. So this side PT is going to be congruent to RT, which is what we've written down over here. Let me write a little neater. RT, and that is by the definition of a midpoint. So we know that these two are congruent. And now that we have our side length, we have enough information to prove that these two triangles are congruent. So triangle PQT and triangle RST are congruent by angle, angle, side. We have an angle measure here, and the side over here. Congruent to angle, angle, and side. So if the side's not in between the two angles, it's going to be angle, angle, side. If it's in between, it's angle, side, angle. Now had this said that T is a midpoint of QS, then that would make QT be congruent to SQ, and that would be true by angle, side, angle. So let's take a look at the next one. Example 6. X is a midpoint of AG and NR. So notice we're getting less and less information as we go through. So I want you to prove that triangle ANX is congruent to triangle GRX. Pause the video and come back and check your answer when you're done. All right, so we have our given statement, X is a midpoint of AG and NR. That's given. Now you can break this up into two statements or you can leave it into one. If you combine this next one, then you only have one reason here. So because X is the midpoint of not only AG but NR, it's going to cut each of these in half, which means that AX is going to be congruent to GX and that NX is going to be congruent to RX. So we have two side lengths here. We have a side here and a side here. So we have AX is congruent to GX, NX is congruent to RX, and both of these are by the definition of midpoint. So that leaves us one other part we have to prove, and we don't know anything about the other side, so we're going to use our vertical angles that are in the middle. Two lines intersect, they form vertical angles, and they're congruent. So that means that angle AXN is congruent to angle GXR. And our reason is that vertical angles are congruent. So this is an angle measure. So we have enough to prove that triangle ANX is congruent to triangle GRX, and our reason is going to be side, angle, side. So we have side, angle, and side. So side, angle, side is our triangle congruency. All right, let's take a look at example 7. 7 is very similar to example 2. We have a parallel line, we have a side that's congruent, and it tells us that we're trying to find that triangle GFK is congruent to triangle KLF. So you got 5 statements and 5 reasons. Pause the video, work this out, and come back and check your answer when you're done. All right, so we got FG is parallel to KL, which is given, and FG is congruent to KL, which is given. So they're marked here, arrows marked parallel, the line segments marked that they are congruent. So the next thing we did is we recognized that if we have parallel lines, we have a pair of alternate tier angles, which means that this angle right here is going to be congruent to this angle down here because it's created from the parallel line and the transversal. So we say angle LKF is congruent to GFK. And it's by alternate tier angles are congruent. Then we recognize that we have a line here, segment, it's a part of both triangles, so FK is congruent to KF by the reflexive property. So that now, right now we have a segment, side length, we have an angle measure, and this is a segment. So, we have enough to prove our triangle's congruent, so if we scroll down here, we got triangle FGK is congruent to triangle KLF, and it's going to be by side, angle, side. We have a side here, angle in between to a side, side, angle, and side. All right, so let's take a look at our last example. Example 8. This one's a little different. It says we've been given an angle is congruent. Angle N is congruent to angle S. And it says that line L bisects TR at Q. Remember, to bisect something is to cut it in half. So it's very similar to a midpoint, although it's not a midpoint. So you're going to be using a definition of a bisector to help solve and prove these two triangles congruent. So pause your video now and come back and check your answers when you're done. All right, so we start off with angle N is congruent to angle S, and that is given to us. We have line L bisects TR at Q. That was also given to us. So we've got the angle N and S are shown congruent. So now, from what we know from that, we also can see that vertical angles are congruent. So angle NQT is congruent to angle SQR. So we name those angles. Vertical angles are congruent. So now, based on something being bisected, since this line L bisects TR, which is this side here, means it cuts it in half, which means that this half is congruent to this half. And so that means we have to name that statement. So T to Q is congruent to R to Q. And the reason is the definition of a segment bisector. So now we have a side, we have an angle, we have an angle. Angle, angle, and a side. That means we can now prove our triangles NQT congruent to triangle SQR by angle, angle, side. So this concludes our lesson on proving triangles congruent using proofs. Tomorrow we're going to look at what happens, or the next lesson we're going to look at what happens when we're going to try to prove where other parts of the triangles are congruent. So we're trying to prove that TN is congruent to RS, or maybe that angle T is congruent to angle R. But in order to do that, we first have to show that our triangles would be congruent. So that concludes this lesson. Make sure you get your homework done.